Welcome to this module of the FinDaS crypto economic course. Today, we are diving deep into one of the most powerful and honestly most misunderstood technologies in the blockchain space, the smart contract. Our goal here is to get way past just a simple definition. We're going to see how these things work from the ground up, from a tiny piece of code to a massive global financial application. By the end, you'll have the solid foundation you need to really analyze this tech. So, here's what we've got on tap. First, we'll nail down the foundational principles. Then, we'll pop the hood and see how these contracts actually execute. After that, we get practical. We'll see how a few lines of code can become a digital token. We'll ground all that theory in a real-world case study on Ethereum, and then we'll wrap up by weighing the incredible applications against the very real risks and limitations. All right, let's start at the very beginning. Because before we can talk about the wild economics of DeFi or NFTs, we have to get this part right. So, what exactly is a smart contract? At its absolute heart, a smart contract is just a program. It's code and data that lives on a blockchain. But here is the game-changing part. It automatically enforces the rules written into its own code. When someone triggers it with a transaction, it just runs, exactly as it was programmed to, without anyone's permission. It effectively removes the need for a middleman, like a bank or a lawyer, to make sure everyone plays by the rules. You know, the funny thing is, this idea is actually older than blockchain itself. A computer scientist named Nick Szabo came up with this brilliant analogy way back in the 90s. He said to think of a vending machine. And it is perfect. A vending machine is a simple, dumb machine, right? But it perfectly enforces an agreement. If you put in the right amount of money, and you press the button, then the machine is physically obligated to give you your snack. There's no negotiation, no one to argue with, the rules are just built into the machine. Smart contracts do the exact same thing, but with digital stuff, using code. So there are three properties that really give smart contracts their power. First, they are deterministic. This is absolutely non-negotiable. If you and I run the same contract with the same inputs, we have to get the exact same result. Otherwise, a global network could never agree. Second, they are triggered. They just sit there on the blockchain, totally dormant, until someone sends a transaction to wake them up. And finally, they're immutable. Once a contract runs and changes something, that change is written to the blockchain, and it's there forever. You can't undo it. Okay, so knowing what a contract does is one thing, but understanding how it runs across thousands of computers all over the world, well, that's where things get really interesting. And that brings us to two core concepts: the Ethereum virtual machine and gas. So where does it all start? Well, a developer writes the contract in a language, usually one called Solidity for Ethereum, but the computers on the network don't actually run Solidity. That code gets compiled down into a much more basic language called bytecode, and that bytecode is what gets executed by something called the Ethereum virtual machine, or EVM. Just think of the EVM as a little isolated virtual computer that exists inside every single node on the network. Its only job is to run that bytecode and make sure it gets the same result everywhere, keeping the whole network in sync. So what does this journey actually look like? Well, it all kicks off when you, the user, send a transaction to a contract to call one of its functions. The network validators then grab your transaction and bundle it into a new block. Then, every single node on the network runs that transaction inside its own EVM. If everything goes smoothly, the change becomes final. But, and this is critical, if anything goes wrong, say there's an error in the code or you run out of fuel, the entire thing is reverted. It's an all-or-nothing deal. So I just mentioned running out of fuel. That fuel is called gas, and it's a crucial concept. Every single little operation a contract does, from adding two numbers to storing a piece of data, has a cost, and that cost is measured in gas. Think of it like fuel for your car. This is so important for two reasons. One, it pays the people running the computers, the validators, for their work. But two, and this is a big one, it's a safety mechanism. It prevents someone from writing a malicious contract with an infinite loop that would crash the whole network, because that transaction would just run out of gas and stop. The actual fee you pay is made of two parts. There's the base fee. This is the minimum price, and it changes depending on how busy the network is. But the really interesting part is that this base fee gets burned. It's destroyed, completely removed from the supply. Then, on top of that, you can add a priority tip. This is basically an extra payment you give directly to the validator to, cut in line. It incentivizes them to include your transaction in the very next block, especially when things are congested. All right, that was a lot of theory. Let's make this more concrete. To really see the power here, I think it's helpful to see how we can take just a few simple lines of code and, with a few clever changes, turn it into something like a digital token. Okay, have a look at this. You really don't need to be a programmer to get what's going on here. This is a super basic smart contract called numbers. All it does is store one single number. And it has three functions anybody can call. One to increment the number, one to decrement it, and one to just see what the current value is. That's it. It's basically a shared counter that lives on the blockchain for everyone to use. Now, watch this. This is where the magic happens. With just 4 logical steps, we can turn that simple counter into a basic token. First, instead of one number for everyone, we use something called a mapping to give every single address its own private balance. Second, we make that increment function private, so only the contract creator can mint new units. Third, we change the decrement function into a transfer function, so you can send your units to someone else. And finally, when we launch the contract, we give an initial supply to the creator. And just like that, we've created a scarce, digital, transferable asset, the core of a token. And that evolution from simple code to a token leads us perfectly into our case study, Ethereum. Now, there are other smart contract blockchains, for sure, but Ethereum was the pioneer. It was the first to create this kind of open, permissionless global computer that let developers build and launch these kinds of decentralized applications. Ethereum launched back in 2015 with this really ambitious vision of being a world computer. Its native currency, Ether, or ETH, is literally the lifeblood of the whole system. You need it to pay gas fees for every single action. It's what's used for staking to keep the network secure. And it's become the foundational money for these massive ecosystems built on top of it, like DeFi and NFTs. And of course, a huge milestone was the merge in 2022, which switched the whole network from the energy-hungry proof of work to a much, much greener proof of stake system. This brings us to a really fascinating part of Ethereum's economy. There are basically two forces pushing and pulling on the total supply of ETH. On one side, you have new ETH being created all the time as rewards for the validators. But on the other side, remember that base fee we talked about? It gets burned. And when the network is really busy, the amount of ETH being burned can actually be more than the amount of new ETH being created. This means the total supply actually shrinks, making ETH a deflationary asset. So, as you can see, Ethereum's economic model has some clear trade-offs. On the plus side, that fee burn creates deflationary pressure, ETH is incredibly useful across the ecosystem, and the network is now very energy efficient. But on the flip side, gas fees can get crazy expensive when everyone's trying to use it at once. And unlike Bitcoin, ETH doesn't have a fixed maximum supply, and its value is really tied to how much people are using the network, which can make it pretty volatile. All right, for our final section, let's bring all this theory back down to earth. We need to take a pragmatic look at the amazing things this technology can do, but we also have to be really clear-eyed about the significant risks and the built-in limitations that everyone needs to understand. The idea of programmable money has just unleashed this incredible wave of innovation. The biggest, of course, is decentralized finance, or DeFi. You've got protocols like Aave that let you lend or borrow money without ever talking to a bank. But it goes way beyond that. You have projects creating decentralized insurance, others building new markets for energy trading, and platforms like Aragon that let people form what are called DAOs, decentralized autonomous organizations, which are basically groups governed by code instead of people. But, and this is a huge but, all this complexity creates massive security risks. Remember how we said smart contracts are immutable? Well, that's a double-edged sword. If there's a bug in the code, it can lead to catastrophic, irreversible losses of funds. The history of crypto is littered with these exploits. Things like reentrancy, where an attacker can trick a contract into draining all its money, or oracle manipulation, where you feed a contract bad information about the outside world to fool it. In this space, security is an absolute battle. And it is so important to remember smart contracts are not magic. They're tools and they have very clear boundaries. For example, a smart contract has no idea what the price of ETH is in US dollars. It can't. It's trapped inside its own little blockchain world. To get any outside data, it needs to trust a service called an oracle, which creates its own issues. They also can't make subjective judgments, they can't force someone to actually ship you a package in the real world, and unless they are specifically built to be upgradable, their code is set in stone, bugs and all. Understanding what they can't do is just as important as knowing what they can. So let's pull all these threads together. At their core, smart contracts are powerful tools for automation, basically agreements that execute themselves. We've seen how they run inside virtual machines like the EVM fueled by gas, and we've seen how platforms like Ethereum use them to build entire digital economies. But we've also seen that this power comes with huge responsibilities, serious security risks, and very real limitations that demand careful, critical thinking. So I'll leave you with a question to carry into our course discussion. Thinking about everything we've just covered, from the simple vending machine to the complexities of DeFi, where do you see an opportunity? Which traditional processes out there, things that rely on slow, expensive middlemen, do you think could be completely transformed by this technology? Think about the benefits, but also think about the new problems that might create. I'm really looking forward to hearing your ideas. Thank you.
If you're ready to go from theory to practice and apply this blueprint to your own project, please visit us at FinDaS.org. We have more in-depth materials and token design support waiting for you.